if they're sort of quick questions, I'm happy to answer them. If you want to, ask me mid-talk. If they're longer questions, maybe I'm planning to try and, keep this to about 35 minutes. And I'm sure we'll have some time at the end to take longer questions or discuss some of the questions. So the topic of the talk is distributed deep learning. And I gave this talk initially at a meetup in San Francisco at our company office. We also host meetups in the deep learning AI space monthly, or not that often, maybe a couple of times a quarter kind of thing. And the topic was generally interesting to people, and so we thought we'd share it with with a different audience. But when I started the talk, I mentioned that, like, one of my concerns about giving talks about distributed anything, whether it's distributed databases or distributed deep learning or distributed processing, is that the topic tends to end up being about neither, because you have deep learning, which as a practice has its own concepts and abstractions and mathematical tools, and distributing it is mainly intended to, like, preserve its behavior but make it go faster or scale bigger. So there's often not much overlap in the, like, there are people who are interested in the core deep learning aspects of the problem, and then there are sort of software engineers, developers who are interested in how you distribute computations or transactions or whatever it is, as a engineering practice, and sometimes the intersection of those two worlds is not very big, but hopefully it will be interesting and something that you will be able to, like, apply to deep learning problems as you encounter them in practice and in production. Let's okay. Hopefully slides are transitioning okay, but this slide is, like, stuck with me. It's a slide. It's a cartoon from XKCD that's probably, like, more than a decade old now, and it's interesting because this was not the original form of the cartoon. The original form of the cartoon was developers waiting for their compilation to finish, their builds to finish. Since then, it's gone through many iterations. At Google, we used to talk about people waiting for their MapReduce jobs to finish when they were processing web scale data, and now this seems to be the applicable to data scientists, where we're frequently waiting on our models to finish training, and so on. And so distributed processing at the end of the day is to, like, shorten this train iterate cycle, scale up to, like, larger problems, and essentially allow us to, like, explore ideas faster. It doesn't really fundamentally change what the tool that we're applying. Mostly we try to apply the tool in a scaled up fashion without affecting its properties of convergence, correctness, and so on. But what I found interesting for this talk is when I look back at, like, distributed computing across different applications, I've sort of seen the techniques go in circles over time. And so I thought I'd share a bit about my history and experiences with distributed processing, and why I think like, deep learning is actually in some ways a return to the past. I started out my first experience with, like, large scale computing at the Supercomputing Center in Pittsburgh when I was working on material science. So we were using the supercomputer to calculate properties of materials. I'll talk a bit more about that. And then from there, I ended up working at Google, worked on search ads targeting, built very simple, at that time, simple models, right? So logistic models, linear models were pretty popular at the time. We had models to predict the quality of clicks, and that had to be distributed just because we were dealing with web scale data. Newspaper digitization, which was OCR at scale. Again, lots of image data, vision data, with using Google's infrastructure to do distribution. One of the major projects I worked on was Google BigQuery. I was one of the founding engineers on Google BigQuery, and two of us built the first version and demoed it at Google I/O, and eventually launched it a year later, and scaled up quite a bit. And BigQuery is Google's Anchor sort of scalable data processing engine. And so there were a lot of interesting problems in distributed computing that were solved there. Um, I worked at a futures trading company, and the modeling there also used distributed processing, but more distributed simulation, which was easy to parallelize, but didn't really fit in the MapReduce framework. At Amazon, there was scale in other dimensions. There was a lot of operations research related, linear programming, those kind of problems that again were not particularly amenable to MapReduce style processing, but they were distributable in other ways. And now I'm at Reality Engines, and we're working on deep learning, and we do use distributed processing, but we use it in many different flavors. Sometimes not ones that you would expect. Interesting thing I've seen through this progression of different frameworks for distributed computing and different approaches to distributed computing is the underlying hardware has gone through a significant evolution over this time, and it keeps changing. Where the bottleneck is keeps moving over time, and this. Hopefully you can read this slide, but I think that it tells us that the slide kind of emphasizes two different things. The bar chart on the right is the different timescales associated with processing and moving data, but scaled up to human timescales. So on the left axis is the actual time it takes. CPU cycle at 1 GHz processors is a billionth of a second, and then all the way up to internet transfers or network transfers and hard disk transfers and so on. So you can see that, like, if you translate it to human timescales, this is really all over the place. Like an L1 cache access is in seconds, whereas in the internet, or let's forget going all the way to internet, but even hard disk IO is approaching a year. So if you thought about this in human timescales, like if you were trying to design human processes, if we had to do a credit card transaction, and a credit card transaction, the time it took us to swipe the card was something like an L1 cache access, but the time it took to actually get confirmation was network, like a hard disk read. It would be like we'd swipe in 1 second, and then we'd have to wait a month for confirmation that our transactions approved. It would make it completely impossible to use credit cards in day-to-day usage. So where exactly, which part of this system is the bottleneck is critical to like whether a system can make progress on a problem. The other piece is that just the rate at which it's changing. When before I joined Google, the 1 gigabit Ethernet was just about becoming a standard, and by the time I left Google, the 100 gigabit Ethernet was getting standardized. So that's a 100x improvement in sort of the network connectivity change. And so one framework for distributed computing might have worked when we were like network bottleneck, but the paradigm which changes a lot as we go to different regimes. So jumping into that timeline, I thought I'd share a interesting bit of an interesting parallel to this deep learning from way back when I was working in material science, right? So in the problem that we were working on in material science is you have atoms arranged in a crystalline structure, an alloy type structure, and you want to find their sort of natural resting position. And how you do this is you have these physics equations that tell you what forces act on atoms. There are some complicated differential equations. The details don't matter too much. You turn them into numerical sort of equations on a grid, and then you have to solve essentially what are these big matrix operations. And so the code looks something like for loops around big matrices in memory, where you do some multiplications, additions, and then finally inversions, matrix inversions, using BLAS and other libraries which are still very much in use even today. And then it spits out an answer, and then you might update the positions of atoms, and then repeat and repeat and repeat until you reach some kind of converged state. The reason I sort of like walk through this is this should, like, for people who are working with deep learning, this should sound pretty familiar, like modern, like training a neural network looks a lot like this. You have uh, your network expressed as a set of weighted matrix connections with some kind of nonlinear function. You take the numerical derivatives of these and you back propagate errors in your training target back to the network, update the weights, take a new data point, repeat, repeat, repeat until you converge, until the weights converge. So actually, you know, this structure for computation is something that is familiar to like many people from engineering applications and so on, where this is sort of the standard pattern. How is distribution handled here? Well, this was a supercomputer. So in a supercomputer, we have really fast interconnects between the different processors. We also have like pretty high bandwidth from the processors to most chunks of memory. But still, the processor runs at like very fast clock cycles, as you saw from the uh, previous slide. So what we do is we divide up the atoms among processors. We assign each group of atoms to one processor. The processor calculates its local state. There's some information that has to be exchanged at the boundary. Hopefully, it's much smaller than the amount of information that each processor has to handle, so that the processor can be kept busy. You run for some cycles, exchange information at the boundary, and then repeat. Again, something that, you know, a pattern that has emerged quite a bit in deep learning. But this was sort of my first large-scale distributed computing application that I was exposed to. And over time, I saw many different forms of these, and we'll talk about some of those. But the key factors to me that kind of stand out in like that that kind of define which framework works the best is a couple of these ratios. So compute time to data exchange time, right? So like if we have to do a lot of compute for a little bit of data exchange, you know, that's sort of one regime. The other regime is like, you know, web scale, where we have very large data and usually relatively simple processing on that data, like maybe searching for a string or, you know, making everything lowercase or whatever. The other is input size to compute time. In many sort of like web scale processing applications, the data size is very large and you have to make one pass through it. So the compute time is not particularly large compared to the amount of data that's processed. Whereas in deep learning, like your input might actually be relatively small. Like explain, you know, you might have a million examples that all fit in RAM, but it takes a long time to actually converge the weights their to reduce the objective function, right, or reduce the loss. And the last is the failure mode, and this is a very important one. And I think a lot of like distributed frameworks have worked around addressing this, and it's no longer very relevant, I think, in our distributed deep learning space, which is dealing with computers that can fail at any given time. A lot of our data center based distributed computing frameworks are designed to recover from partial failures of individual nodes and so on. This is important if like your, again, problem is so big that like small failures are likely to occur and you don't want them to like fail the whole computation. Then you have to have support in your infrastructure for being able to retry individual like sub components of the problem. If you don't have that failure mode, this actually adds a lot of overhead and cost and complexity that is, you know, that actually ends up being a drag. So that brings me to this topic of MapReduce. MapReduce is, I would argue, like has dominated distributed computing as a conceptual paradigm for like about a decade. Like ever since like the Google paper came out, and like web scale processing has become important for like a number of applications and companies. uh, MapReduce and its public form of like, you know, Hadoop, and then its eventual evolution to Spark have uh, been one of the key areas of like work on distributed processing and support infrastructure for distributed processing. Uh, and we've turned a lot of our problems, like even SQL is now like essentially executed underneath as like these MapReduce style operations. Now, of course, Spark and all generalize the notion of like what is a map and a reduce, but conceptually, like it shares a lot with the basic principles of like the, you know, original paper. And the thing that's interesting is that that paper created MapReduce to work around some like very specific problems. One of them was like cheap hardware. Google invented this at a time when they were running data centers where component failures were very common. It was not unusual to have any 2-hour long job experience multiple individual node failures as the computation was progressing. So failure fault tolerance was really important. Data center networking, as I mentioned, data center pipes were small, like between computers and data centers, and so the network was a bottleneck. This required things like moving the computation to the data rather than shipping the data between nodes. Spinning disks were another constraint. A lot of data was coming off of hard disks, and as you saw in that, hard disks are slow compared to RAM and really slow compared to processors. So it was very important to sort of make the maximum use of your hard disk as far as possible and avoid intermediate data going back to disk. And the last was just the data scale explosion. There was definitely, with the advent of like web-based applications and very large user bases, companies were dealing with like very large volumes of data, and that required a data processing framework that could move a lot of data through a computational framework. Sorry, let me go back a second. So the 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 point I want to sort of convey here is that like MapReduce was very relevant at the time it was invented. It gave rise to a lot of useful frameworks, but I think there's an aspect of like this general approach looking like a hammer and everything looking like a nail. And so I think applying it to many data science problems, sometimes like even sklearn and support deep learning on Spark. Uh, this is one way to sort of scale up your computation, but often they add a lot of overhead that's unnecessary and are not really the issues or bottlenecks in deep learning. So I would caution against like continuing to be tied to this approach for processing. So again, so I want to make a brief detour here and talk a little bit about a component in Google to kind of illustrate like how powerful MapReduce was as a conceptual thing, right? So for those of you who are familiar with Google BigQuery or potentially Presto, which is like an open source version of it, there's Drill, Apache Drill, which are all basically variations of like online data analytic engines that can perform a wide range of analytic queries, generally those that can be expressed declaratively through SQL or any flavor of SQL. They can execute them very fast because instead of like MapReduce like spinning up a job, they're not job oriented. They're sort of this multi-tenanted architecture where data is flowing through a set of servers that are ready to process the query and to split up the query dynamically. So the original implementation of this structured the whole service in this three-tiered architecture where there was a root at which your query was presented, the query was planned and then dispatched into like a set of intermediate layer which could fan out the operation to a leaf nodes that ran the computation and were also close to the data, and then that they sent up intermediate results back to the mixers, which did some aggregation and finally returned some small response to the root. And it's interesting that despite this being such a different architecture with such a different goal, it was actually heavily inspired by MapReduce. The structures lined up with the controller, reducer, and mapper, which are the standard components in MapReduce style frame in the original MapReduce paper and framework. So this approach to building distributed processing frameworks impacted a lot of distributed design over time. But the data center itself significantly changed over this decade. That made the MapReduces like sort of focus on like efficient movement of data much less important. One of the major sort of advances was the arrival of significantly faster networks and very large switches. So in a standard data center now, like Google's data center or Facebook's or most large companies, they have these bisection networks that achieve um, up to 10 gigs of bandwidth between every node, even if there are 100,000 machines in the data center. So the switches are able to like connect in a sort of n squared fashion all of these nodes at 10 gigabytes per second. And even with 1 giga core speeds, if you work through the math, at about 10K cycles per record, which is a fairly small amount of cycles, which you're doing very little processing, you can put out 1 KB records at 100 megabytes per second. And those can easily, even if you have 100 cores on a node, you can ship them between all of the nodes in the network. Basically, what this means is that we no longer have to worry so much about moving data. It's become much cheaper to move data, and so you can design your distributed processing framework in a way that, at least like CPU clock cycle speed, you can much more freely move data between nodes. And like the design of Spark and other systems now rely on this heavily, where intermediate data lives in any node, and as the computation plan progresses, the data is shuffled across the different nodes to achieve the computation. And it's much more efficient than sort of doing shuffles to disk, or having to force data to a specific node. But again, this data center, like this data transfer gains that came with respect to the CPU were short-lived, because now the GPU has once again changed the equation, where we're back into a place where we can do a lot of compute uh, beyond what we can actually transfer in and out of like the device doing the computing. And in this case, it's the GPU. So this is just one example. This is of course the top of the line, like Tesla's V100 chip, but it's quite remarkable if you think about the numbers and the progression. So the V100 chip is rated at like 100 teraflops, and 100 teraflops is, when I mentioned I was at Pittsburgh Supercomputing, more than a decade ago, but around mid 2000s, and the Pittsburgh supercomputer did not have 100 teraflops, and it was composed of many, like a few, like I think 1,000 CPUs roughly. So now we can fit like 100 teraflops into this one card. We get boxes that have 8 of them, and this box with 8 of these cards is $100,000. And why do I mention the cost? Well, if you remember, I said that like previous distributed computing frameworks worked very hard to avoid node failures, like to work around, to be fault tolerant to node failures. uh, well, if you have $100,000 box, a node failure is not something that you really tolerate, right? Like it's, you expect, you expect that to be such a significant cost, and you expect it to be alive, or you can afford to build it within hardware that is very reliable. And so mostly, even if your computation lasts days, you can expect your computers to run without any issues. It's not worth being fault tolerant in this case. But what it does is, what you do have to solve now is how to keep these machines fed with data so that they can use this full 100 teraflops. So now we're kind of getting into the deep learning space. So let me sort of like mention sort of like some of the bread and butter issues that come up with distributed deep learning, and what are sort of the critical things. So now we don't necessarily have to think about deep learning at the context of distributing it across multiple machines. We have multiple GPUs in a single box. We can have a few of these big boxes, and they are capable of training like very large models, just because of the compute capacity we can fit into an individual box. But we have to be cognizant of like the memory bandwidth bottlenecks that now exist when we're using such so much, we have so much computing capacity on tap. So one of the key sort of things we pay attention to is how much data we move in and out during the model training cycle. And a common problem is for like images and video data. Like if you're training with mini batches, you can easily become bottlenecked on getting the image in and out of the GPU with each mini batch. So if a particular image is going to be trained over multiple times, which is common when you're training for multiple epochs, it's much more efficient to make optimizations like putting all of those images on the GPU upfront, and then generating the batches with only references to the memory living in the GPU, so that you're not actually transferring memory in and out of the GPU. An example of this, which we used recently for video, is we loaded a full 8 GB video into into the GPUs for training, and then just reference slices, three-dimensional slices in time and space of the video to construct the mini batches. So that avoided trying to construct and extract that on the CPU and push it in. The CPU only coordinated what slices to take in each mini batch, so much less data was flowing in and out of the GPU. So these are the kinds of approaches that are becoming important in GPU dominated processing, which deep learning is the prototypical example. So before we jump, the rest of the talk we sort of get more into like techniques and experiences I've had with deep learning that have allowed parallelization of deep learning jobs. But I want to summarize sort of the first half of this by saying that we've kind of we go through these cycles where compute or transfer are the dominant bottlenecks, and we have to make sure that we're using the right framework for the bottleneck that's like relevant to the problem and hardware of the time. And what I'm noticing is that in the deep learning space, the patterns that are worth following actually come from when supercomputing are more commonly applied in the supercomputing space and are appropriate again, but are not necessarily very common. There's not as much experience with them because we're coming from a time when MapReduce style distributed computing was standard. So in distributed deep learning, there are sort of two basic approaches to achieving parallelism and being able to concurrently utilize processors. There's model parallelism and there's data parallelism. I'm not going to focus much on model parallelism. Let me just quickly, tell you why I'm not spending too much time there. There's firstly quite a bit of confusion around the term, because model parallelism is used to solve two different problems, and they're sometimes confused. One is when your model is big enough that it doesn't fit, or your model plus training data is big enough that it doesn't fit in a single GPU. So you have to utilize multiple GPUs just to be able to manage the scale of data that you have. In this case, you're not really getting parallelism because you're not necessarily concurrently executing on both GPUs. The output of the one GPU might be waiting for like the other GPU to finish. So you get like 50% utilization or something. But just because your weights or size of the model doesn't fit in a single GPU, it forces you to like spread the model over two GPUs. There are models that can be designed that actually can evaluate concurrently, and CNNs are a good example where you can have different parts of the image being processed on two different GPUs at the same time, but it means processing very large images and designing a network in a way that it is able to achieve that. So I actually think that in practice, this is not something that people run into much or encounter much in achieving training parallelism, at least. The other one is data parallelism, and data parallelism is just parallelism around the training examples and feeding them to a number of distributed, like otherwise disconnected learners, but then synchronizing the learners either in an asynchronous manner or in a synchronous fashion where weights are exchanged and updated based on the deltas seen across the set of examples. So data parallelism is relatively common and relatively important to exploit, because we often have problems where the size of the training data itself makes it challenging, makes it prohibitively slow to train on a single machine. There are a couple of different tools and so on showing up in this place. The symbol here that people might not recognize is OpenMPI. MPI has been a standard since like supercomputing and is a standard for exchanging large buffers of memory in a sort of principled way. NCCL is NVIDIA's extension of that is used that they've optimized for their NVLink infrastructure for cross GPU interconnects and so on, so that you can share data directly from GPU to GPU. And Horoward is one example of a distributed update framework. It's from Uber, and it uses the idea of sharing the gradients as part of the updates between as the models progress, rather than averaging the parameters, averaging gradients. So I want to go into like one specific example of like where like the kinds of problems that need to be solved for distributed deep learning to be, well, for distribution to be effective on deep learning. This was a problem that we were working on actually at Amazon, and it involved a deep learning model where one of the inputs was a zip code. So I don't want to talk too much about specifically what we're predicting because that's Amazon specific, but you can pretty easily imagine the problem. There's some target that you have to predict. In this case, it was not a classification problem. It was actually more like a regression problem. And you have a number of input features, and one of the input features is zip code. And zip code is a high dimensional categorical feature. In the US, you have about 40,000 zip codes. There's no real structure to them. Zip codes can actually be non-contiguous. They can, next neighboring zip codes need not have neighboring numbers, and so on. So they're best modeled as a categorical. And so we used an embedding layer to between the zip code feature and the hidden layers of the model. It was a standard feed forward network. So what we found was that we could train the model had very good performance. We could train it on our data set and get useful accuracy and performance from the model, but it took about a week to train the model, right? And not a week, but probably maybe 2 to 3 days to train a model on a single machine, which is long and slows down the iteration cycle for testing with features or testing with new data, or generally experimenting with the structure of the model. So you can imagine waiting a few days is painful. So we decided to try parallelizing the model, and what we found was pretty poor scaling and performance. What was happening was the model would converge even with multiple GPUs, but it would not converge. The rate of convergence dropped a lot as we added more GPUs into the cluster. So we were getting some speed up, but very sublinear, and we could never really cross like the day barrier, even with 8 GPUs, which is surprising considering throwing 8 times the compute, getting like nowhere near that performance. So what was happening is we were actually affecting convergence itself by distributing the training examples across different machines. So what we decided to do was we looked at the problem, and what we had the intuition that like what was probably going wrong was the handling of the zip code embedding layer. So we were using mini batches. Mini batches in distributed training become micro batches because you kind of split up the batch further by the number of GPUs that you're going to throw at the problem. Each GPU does its computation, and then you average the gradients that comes back from each one, and then repeat with a new set of micro batches at each GPU. So zip codes being 40,000 of them, and the micro batches being fairly small on order or like 20, 30 examples per micro batch, you'd have very non-uniform distribution of zip codes. So some of the nodes would see some zip code. Each node would see kind of like a small subset of the zip codes, and its gradients related to that embedding layer would then be averaged out with the other nodes that saw a completely different set of zip codes, most of which would not overlap, right? So our intuition was that this zip code embedding layer was not converging. The zip code feature was very significant. We knew that geo was an important feature for the model that we were trying to build. So with the zip code embedding layer not converging, all the other layers, the hidden layers weights were also not converging, because one of the input layer weights itself was converging very slowly. So we thought our intuition was that the convergence was being affected by the sampling noise around micro batches and having to average across different batches that were seeing different distributions of zip codes. So what we did was we changed the scheme used for averaging to a somewhat non-standard, or I would say a fairly non-standard approach. I've not seen it documented in any library, but what we did was for the zip code input, which was going into the embedding, at each node, we also accumulated the sum of the zip code seen. And so in this case, since it was, a categorical embedding, you basically have a 1 for every zip code that shows up in that particular input. And so if you saw 10 inputs and you saw zip codes 1, 2, 3, and 4, you'd have a 1 at each of these locations. So we summed the weights across all of the inputs seen in a particular micro batch, and then return that sum along with the gradient, right? With the micro gradient computed at that worker. The controller then used this weights returned when doing the averaging. So for the embedding layer in particular, it used the weight vectors of the zip code seen to average the gradients for the embedding layer. And this way, like if a particular node saw a zip code and no other node saw that zip code, its updates to the zip code weight would be significant, but it wouldn't basically become 1/8 because you had 8 other nodes that did not see the zip code and had a 0 gradient for that zip code. Um, it turned out that this helped quite a bit. You can see the graph, the weighted graph on the right. We still didn't get like linear convergence. It's fairly rare to get linear convergence in linear scaling in convergence when you distribute deep learning problems. But this is not bad. Like we could get a model down from a day or multiple days to a couple of hours, which helped with iteration speed quite a bit. This is, I would say, the interesting direction for research in like distributed deep learning, right? So there are many interesting ideas coming up in this idea of like how you combine gradients from multiple workers that are all updating the same model. Another interesting one that I encountered fairly recently was Hidasam. It's part of the Horoword framework that I mentioned. That's from Google. It's been contributed to the Horoword framework. And what it does is it tries to combine gradients in a way such that it doesn't undercount or overcount gradients from different nodes. So what it does is it looks at the gradient for a particular weight from each of the nodes, and if the gradients are largely aligned, then it does averaging. But if the gradients are orthogonal, then it does something more like addition. The mathematics of this is it projects one gradient onto the other gradient and then sees and keeps the perpendicular component of the second gradient. And it does this iteratively across, it recursively sort of like collapses the gradients from each of the nodes coming back. So what this does is if you have, if all of the nodes saw similar sort of data and they all wanted to take a step in the same direction, you don't end up taking a very big step because you just added up all the gradients in the same direction and end up maybe overshooting or whatever. So that's the first case in the upper diagram. And then if they saw sort of different data that let them update weights in different dimensions, then you can add up the gradients and you don't just do simple averaging, which would reduce the impact of some of the dimensions a lot, right? Like you would get a very small contribution from G2 if you just averaged it. So that's useful. It doesn't quite solve the zip code problem because it's not input sensitive, so it doesn't distinguish whether G1 and G2 saw a similar input distribution or not. But in an input independent way, this is a useful approach for speeding up convergence when you distribute training. So the it turns out that with this setup, because you're dealing with these really powerful nodes, maybe multiple GPUs on a single node, and you have to feed them with a lot of data, and there's not much chance of failure. You don't have to worry about failure domains as much. That you don't need the complexity of complex distributed computing frameworks, MapReduce, Spark, other such ones that have a lot of coordination, a lot of logic around how to where data is existing and where data has to move between which nodes and so on, because the focus of the problem is on keeping these large compute nodes fed with data, and in this case we can use like much simpler distributed processing setups. We leverage Dask quite heavily. So we do use Spark for like preparing data upfront, right? So like when we need to, combine, join, merge, clean data before assembling the data for the training, we use Spark. It works well still in those cases. But once we have the data produced for training, we can just have Spark give us, either 10 separate pieces or in a format that allows subsets of the data to be accessed efficiently, and then simply parallelize it using a framework like Dask, which launches a set of end workers. Each of the end workers might be on the same machine and access one given GPU device on the same machine, or spread across multiple machines. And the network doesn't actually flow between the master and the controllers. They can access the data directly from some cloud, so either S3, HDFS, doesn't matter. But they have a very simple processing pattern. It's just, you tell me a batch to train on, I go and spend the next minute processing that batch, build some gradient or some small amount of data that has to be returned. That data can be returned and exchanged just between the controller and the workers without overwhelming them, and then repeat until we begin to get convergence. The controller detects convergence. So we don't have to worry about locality, failures, sorting. So I must mention, sorting is probably one of the key things that like the MapReduce and Spark solve when you do a reduce operation to like sort inputs into the set of all inputs of the same key. So that whole infrastructure drops away. And the key thing we focus is on exchanging as little data as possible without impacting the convergence rate for our model training. Let me see. I am actually running long on time, right? I'm going to maybe run through the last slides just so I leave a little time for questions. The other approach that we use a lot at Reality Engines is we actually just do more in the sense that instead of trying to train the same model faster, we train N models in parallel to do hyperparameter optimization or network architecture search. There are many approaches out here that, simple embarrassing parallelism allows you to do interesting things outside of like optimizing the convergence rate for a specific model run. The other piece is actually, I'm going to skip the slide just because we're running tight on time. But like, I just wanted to mention that like inference is a completely different story, and there's a whole area of research around that, and solutions that you would try if you want to speed up or parallelize inference. Very different from training, so kind of outside the sort of this thing of this talk. So let me sort of wrap this up with the conclusion saying that like I actually think it's fortunate that we're like faced with these problems, because in some sense from a modeling perspective, data science perspective, it's much more interesting to work on problems and techniques for like handling convergence rate and managing the movement of this data in a principled fashion than actually with infrastructure code that is more about shuffling and moving data between nodes and being worried about network transfers and recovery and those kind of logical distributed problems. I think there's a lot of patterns from supercomputing that are relevant that we should go back to and refer to when designing our faster training methods. And then lastly, based on my last slide, like instead of trying to speed up the training of individual models, we should focus on automated model exploration so that we can simply use extra computers to explore the space of models in a more hands-off manner rather than having to be involved in the model exploration iteration loop. So that was my last slide.